Empirical formulas. Formulas represent mole ratios, and an empirical formula is going to be the lowest whole number ratio. Now, when we talk about whole number ratios, the ratios that I have here, I've got a ratio of 2 to 1.25. I want a whole number ratio for that. The 0.25 represents a quarter, so in order to get rid of that denominator, I want to multiply both of these by 4. 4 times 2 is 8. 4 times 1.5 is 5. So this becomes an 8 to 5 ratio. For the 1.33 to 1, 1.33 is 1/3. So I need to multiply both of these by 3. This ends up being a 4 to 3 ratio. 1.5, 2.25, 2.00. Well, I've got a half and I've got a quarter. I need to multiply by 4 to get rid of the denominators. 4 times 1.5 is 6. 4 times 2.25 is 9. And 4 times 2 is 8. So a 6 to 9 to 8 ratio in whole numbers. And for the last one, 0.67 is 2/3, 0.25 is a quarter, and 0.33 is a third. The lowest common multiple of these is 12. I need to multiply each of these numbers times 12, and I get 32 to 15 to 16. So I get a much larger ratio, but I finally get them into whole numbers. When we are looking at these fractions, we are hoping to find fractions that are close to 1/2, 1/3, 1/4, and rarely higher than that. You may see 1/5, but I highly doubt it. You're going to have some pretty clean data to work with most of the problems. Now, when we're looking at an empirical formula, if you look at the subscripts on this, you'll notice that they are all divisible by 6. So the empirical formula for glucose is CH2O. And of course, these are called carbohydrates with carbon and then water. And part of the way we're going to use empirical formulas is that when we have that lowest whole number ratio, we can do an empirical math for that. And so we have 1 nitrogen at 14. We have 2 oxygens at 16. So we've got 14 plus 32 is 46. If someone independently solved for the molar mass and it was 92, you should be able to see that that is twice as big as your lowest whole number ratio. But you can actually take the molar mass and divide it by the empirical mass to get a factor. And for us, this would be 92 divided by 46, which would give us a factor of 2. This 2 will be multiplied times the subscripts. So the actual molecular formula here is N2O4. It's twice as big as the empirical formula. And this is how we're going to be able to go actually from mass percentages to formulas, at least empirical formulas, and maybe molecular formulas. Remember, if it is an ionic compound, we will probably stick with empirical formulas because ionic compounds are merely ratios. Okay, so if you go to the next page in your book, and this might be 40 in the handout section, you will see an example of using this. And we will actually be using something pretty similar to the flow chart that is figure 3.5 in your book. We will take the mass or the percent composition, and we will divide that by the molar mass to get moles, and this will actually give us a ratio, but it will be usually a little messy. We will divide it by the smallest number of moles to get something that will be close to a whole number ratio, and we may need to fix it a little bit, and ultimately we will get a simplest formula, which is your empirical formula. So let's take a look at this. I have 3 problems here, and going through the first problem, it says that we have 4 grams of bromine, and they react completely. So we're going to put all that bromine in the compound with excess fluorine to make a compound that weighs 8.75 grams. So 8.75 grams includes both bromine and fluorine. 4 of those grams are bromine, so the other 4.75 are fluorine. We are going to turn those grams into moles by dividing by the molar mass. The molar mass for bromine is 79.90, and for fluorine it is 19.00. And I'm getting these molar masses from the textbook. So if I divide 4 by 79.9, and notice I didn't put those zeros in because they do nothing mathematically in calculating. And I'm going to use at least 3 significant digits here. And then for the other one, 4.75 divided by 19. Okay, and that would be the moles. You can already see that this is close to a 1 to 5 ratio, but we are going to take the smallest number and divide by that. So both of these numbers are going to be divided by 0.0501. Now the whole key to this is one of these should come out to be 1. Don't know which one. You don't always know which one, but that lowest one should come out to be 1. And then I will take 0.25 and divide it by 0.0501. Enter. And I get 4.99. Well, this is not exactly a whole number, but it is awfully close to a whole number. So I'm going to round that up to 5. If it was 4.75, I would deal with it as a fraction. If it was 4.95, I would round it up to 5. So sometimes you have to use your judgment here. There is no factor needed. I don't need to go any further. And the formula for this compound is I've got 1 bromine to every 5 fluorines. And this is my empirical formula. Now, let me mention something that happens with the last one. And the last one is going to do 2 things. I'm going to skip this one. You can practice on this yourself. You should get K2CrO4 when you're done. And you will not need any factors. You should not need any factors. For this one, we've got a little bit more information and a little bit less information. We have got C, and we're told that that is 49.3%. We've got H, which is 6.9%. And then we have O. It doesn't tell us how much, but if we take the 49.3 and add the 6.9, 9 to it, we have a total of 56%. Well, guess what the other is? It's oxygen. So I am going to simply find the difference. Whoops. I'm simply going to find the difference from 100, and so I just subtracted 100 from it, and the difference is 43.8. Now, percentages don't look like grams, but your assumption here is that you've got 100 grams of your compound, so 49.3 grams of that is equal to the grams of carbon. And this allows you to change grams into moles. The molar mass of carbon is 12.01. For hydrogen, it's 1.008. And for oxygen, it's 16.00. When we divide by each of these, so we've got 49.3 divided by 12.01. Whoops. I get 4.105. If I take 6.9 and divide it by 1.008, I get 6.845. And if I take 43.8 and divide it by 16, again, I got to get all these numbers right. I have 2.738. Well, the smallest number is 2.738, so that will be my divisor for each of these. And the oxygen will be the 1 out of this, so 4.105 divided by 2.738, and this is 1.499 and 6.845. Whoops. I went too far. 6.845 divided by 2.738, and I get 2.5 here. Okay, this number is very close to 1.5. I'm going to use a factor of 2 to get rid of the 0.5s. 2 times 0.5 is 3. 2 times 2.5 is 5. And 2 times 1 is 2. So my empirical formula is C3H5O2. And to get my empirical mass, I'm going to have 36 grams of carbon, I'm going to have 5 grams of hydrogen, 32 of oxygen, which is going to give me a total of 73. And my molar mass was done independently at 146. If I divide my molar mass by my empirical mass, I get a factor of 2. So I'm going to multiply all of these times 2 to get my molecular formula. And the molecular formula will be C6H10O4. So we needed a factor because our ratios were not whole numbers. And then we could actually get the molecular formula because we have a molar mass to compare it to. So this one goes a step further. So this is an example of using empirical formulas and molecular formulas.